Thus far, we talk about hydrogen as a modeled atom, and mainly because hydrogen has one positive charge and one electron. So it simplifies some of these concepts. Beyond hydrogen, we have many electron atoms, basically an atom with more than one electron, such as helium. Now, helium has two positive charges and two negative charges, which introduces another level of complexity, because technically helium is already a many electron atom, not to talk about lithium, which adds yet another whole level of complexity there. So when we talk about many electron atoms, it becomes increasingly more difficult to find the exact formulas to um, describe the system using Schrodinger's equations. You don't need to be concerned about that. But you need to know that for inorganic chemistry, for practical purposes, for many electron atoms, we rely on what's called orbital approximations, which are computational methods that we use to describe the atomic or orbitals that resemble that of hydrogen atoms. So let's introduce a concept of penetration and shielding. So when talking about helium, it is relatively easy to account for the electronic structure. So we have, for practical purposes, we have both electrons that occupy the same orbital. They have the same spherical shape as hydrogenic 1s, right? This is the 1s orbital. However, hydrogen has one electron, helium has two electrons. Because of these two electrons occupying the same orbital and the nucleus in the helium having one extra charge, it is intuitive to think that the orbital in helium will be more compact, because the electrons would be drawn towards the nucleus more closely than by the one proton in helium. So why? Because again, the two electrons in helium are on the same orbital, same level. The first orbital, the 1s, just like the hydrogen is 1s. So there is nothing in between the nucleus and the electron. So they're in ground state configuration. And for helium, the ground state would be 1s2. Now, this is relatively simple. However, when we go beyond, when our Z, the charge, becomes 3, which is in the case of, well, the next element, lithium. Obviously, we know that the configuration 1s3 is forbidden. And this is a fundamental feature known as Pauli exclusion principle. Pauli exclusion principle states that no more than 2 electrons may occupy a single orbital. And if 2 occupy a single orbital, then their spins must be paired. What does that mean? Remember the spin. The spin is the ms, and it could be either positive 1/2 or negative 1/2. If you do not remember this, please refer to the previous lecture. And remember, this is also the spin is also represented as up and down arrows. So if one electron has a spin of 1.5, then the other electron will have to have a spin of negative 1.5. So altogether, I hope you remember that the state of an electron is described by 4 quantum numbers, the n, l, m, l, and ms. And furthermore, the Pauli's principle states that no two electrons can have the same 4 quantum numbers. Remember, this is very important. And why? Because based on certain observations, we in spectroscopic studies, we've seen that there are certain transitions that do not occur in helium. Therefore, Pauli came up with a principle that states that this is true in which n, l, ml, and ms quantum numbers cannot exist for two different electrons. So knowing this, we know that we can deduce, I suppose, that 1s3 orbital is forbidden by this exclusion principle. Therefore, the third electron must occupy an orbital that is of higher shield, just like in the case of lithium. So we have 2 electrons in the first orbital, and we have the third in the second orbital. Now, the question is whether this second orbital is 2s or is it 2p? So, in order to answer this, we need to examine the energies of the subshells and the effects of other electrons in the atom. So we know that S2 and the 2s and 2p orbitals have the same energy in hydrogenic atoms, right? The calculations show that this is not the case in many electron atoms, right? So in hydrogenic, in which we have one electron, that holds true, but that does not hold true in many electron atoms. So let's see why. So when we begin talking about the attractive forces of the nucleus and repulsive forces of the negatively charged electrons around it, we approximate the negative cloud, if you will, around the nucleus. And because in simple systems we have spherical distribution, we can assume that the field is generated by a point source in the middle of the sphere. So for any given point, we have the attractive forces of the nucleus, the positive charge, and the repulsive forces of the electron cloud, which is evenly distributed. Therefore, the negative charge basically reduces the Z value, the charge value. So we go from Z value to basically effective Z value, Z effective. So it would be the effective nuclear charge. We know that the nuclear charge depends on value of N and L of the electron that we're talking about, because the electrons in different shells and subshells approach the nucleus to different extent. We know that from the models. Therefore, this effective reduction of the nuclear charge in different nuclear levels by other electrons that are involved and then have the repulsive forces is generally called shielding of the charge, or just shielding. Due to the shielding effect, the effective charge would be always less than the actual charge, and it is written as the Z effective equals to Z, the actual, minus sigma. And sigma is a certain constant that is empirically calculated. Now, it is intuitive to see that the closer an electron can approach to the nucleus, the closer the Z effective value is to Z, because there is less of a repulsive effect by other electrons, right? So let's consider the 2s electron in lithium. There is shall we say, a non-zero probability that 2s electron can be inside the 1s shell. So the 2s electron can find itself in 1s shell. Now, think about what this happens. The electron does not occupy the 1s, but it can be within this probability distribution. So the potential of this occurring is known as penetration. Okay? So now it is important, and the penetration in this graph is highlighted here. Now it is important to remember that the 2p electrons that will not penetrate effectively through the core, because, as we have stated already, the p orbital, p electrons wave function actually goes through zero in the nucleus, right? So in a many electron atom, the 2s electron has altogether lower energy. It is bound more tightly to the nucleus than a 2p electron. Therefore, the 2s electron will be occupied before the 2p. So therefore, giving the ground state configuration of lithium being 1s2, 2s1. So the 1s orbital is filled, and a 2s orbital has one electron. Okay. Another way to write this is helium 2s1. Why? Because helium is 1s2. 2 electrons in a 1s orbital. Now we can say that 2s has lower energy than 2p orbital, and more generally, any ns will have any np orbital, n being 2, 3, 4, and so on, in any of the many electron atom many electron atoms. So the s orbital in the outermost shell of an atom is generally less shielded than a p electron of that shell. So now let's look at this. So the z value for let's say carbon, as we know, is 6. Now one s orbital is shielded, and the z effective is 5.67. The 2s orbital is even less. 2p is even less. Now if we go into larger atoms, such as, let's say, chlorine, which has a z value of 17. As we go to the first, second p, third s, third p, it is successfully reduced in magnitude, and this is because of addition of negative charges that shield the next orbital. Basically, it effectively reduces the z value. Here is a general outline of how the effective z value changes throughout the periodic table as the atomic number increases. The effective energy decreases. Why? Because of additional electrons, it gets larger. Now, we have an interesting phenomenon here in which in this insert we have this sharp decline, and that is because this is where we start seeing the z equals 20. And if you put everything together, filling in the orbitals, as if you go through it, you will see the 1s1, the 2s2, 2s1, the 1s2, 2s2, 2p, and so on and so forth. This actually, this corresponds to z being 20 and basically the appearance of the 3d orbital. Knowing the ground state electron configuration is very important, but we cannot calculate it. It's very complex. So, but we can determine it experimentally through spectroscopy. For that, we need to consider both penetrance and shielding effects. We have to consider the Pauli exclusion principle. And with that, we can determine the plausible ground state configuration. So let's talk about the ground state configuration. Now let's see how we can apply the buildup principle to infer something about the ground state electron configuration. In the buildup principle, atoms are treated as being occupied in an order that is partially determined by the principal quantum number and partially by penetration and shielding. So, order of occupation is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Now, is the quantum, the principal quantum number, as well as penetration and shielding. So, we know that each orbital can accommodate up to 2 electrons, each orbital. And we know that the p subshell has 3 orbitals. Therefore, the p subshell can accommodate up to 6 electrons, right? And there are 5 orbitals in a d subshell, 5 orbitals, therefore it can accommodate 10 electrons. So, having said that, let's look at the first 5 elements in our periodic table. Hydrogen, it has in a 1s orbital, we have 1 electron. Helium, 1s orbital, 2 electrons. Why? Because the orbital can the s orbital can only sustain 2 electrons. Then lithium, we have 1s with 2 electrons, we have 2s with 1 electron. Then we have 4 electrons here, 1s and 2s are complete. Then for barium, we have the 1s, 2, 2s2, these two orbitals are complete. Then we start filling the 2p orbital. And we'll start filling this for the next 5 elements up until we have 1s2, 2s2, 2p, 6. We have experimental evidence that show that the above is accurate. So when we have more than one orbital that is available to be occupied, such as in the case of 2p orbital in boron or carbon elements, we use the following principle. Basically, if we have more than one orbital with the same energy, electrons will occupy several separate orbits and have the same spin, ms value, in parallel. So it is said that they will have parallel spins. So the occupation of separate orbitals of the same value L is weaker than those that occupy the same region in space. Right? That also makes sense. We have negative charges that repel each other, and if they're further away, well, guess what? They repel each other less. Now, there is a whole theory around it that spans from quantum mechanics, which is called spin correlation. We're not going to talk about it. But the idea is that there is a tendency of two electrons with the parallel spins to stay away from one another. If they stay away from one another, they repel each other less than they would if they were in the same orbital, obviously. Energy exchange has a profound effect on stability. Whenever we have electrons in parallel spin, it is a stabilizing arrangement. As we've noted in a previous slide, this is because the parallel spin configuration, let's say in this case ms 1.5 and another ms 1.5, comes from the fact that these two electrons are indistinguishable and are readily interchangeable. Therefore, now remember this interchangeability and indistinguishable nature of these electrons. If we remove one of these electrons from this pair, this interchangeable nature is lost. Therefore, the exchange energy is lost. What does this mean? We can infer that in the electrons in degenerate orbitals, what does degenerate orbital mean? It's just a electron orbital, any electron orbital that has the same energy level, are generally known as degenerate orbitals. So degenerate orbitals with large number of parallel spins are more stable compared to those that do not have these properties. Therefore, the highest exchange energy occurs in half-filled shells within a large number of electrons with parallel spins. So half-filled shells, such as D5 and D7, we have, remember how many we could have in a shell? Well, we have half-filled, one only. So we have a stable arrangement with this parallel spin configuration. A removal of an electron from this configuration actually will require an input of energy to overcome this great amount of exchange energy. So, for example, a removal of electron from D5 configuration. Here we have 5 electrons in that have the same spin, which we remove one, it will give us 4. This effectively reduces the number of pairs of electrons from parallel spin from 10 to 6. Okay? It's not going to happen readily. So let's look at a prime example of chromium atom. Now we would expect chromium to be 4s2 and 3d4, right? We would have to complete the shell before going on to the next shell. However, as we see here, D5 is more stable than D4. Therefore, the chromium is actually 4s1 instead of 2. And the next electron is put into the d orbital. If we remember from previous lecture, the p orbital has subshells. Now the question is, which subshell is occupied first? It's arbitrary, because p orbital is of the same energy, because these are, well, therefore they're degenerate. But as a conventional rule, we represent them as px, y, z in alphabetical order. So the ground state configuration of carbon would be 1s2, 2s2, 2pxy1, 2yp1, but for simplicity purposes we write it as 2p2. Now carbon has a helium core, which is 1s2, and then we have 2s2 and 2p2, which we can represent as valence electrons, right? 2 pairs of s electrons and 2 pairs of p electrons surrounding the helium core. Okay. Now carbon, nitrogen, we have 2p3, oxygen, we have 2p4, fluorine, we have 2p5, and then neon, we have 2s2 and 2p6. Now neon is also a closed shell. The configuration of neon is basically 1s2, 2s2, and then 2p6. So this is a neon, and anything that comes beyond neon, we can use neon as a core instead of helium in a case of carbon, nitrogen, and oxygen. I hope that makes sense, because if we start getting larger and larger and be needing to write this whole thing out, it will become just too cumbersome. Therefore, just using a neon for this whole thing becomes a lot more easier. So for example, let's look at sodium. Sodium is basically a neon plus an electron, right? One more electron, not quite plus electron, but so we can represent that as a core neon and then 3s1, right? So instead of writing 1s2, 2s2, 2p6, and then 4s1. Now, the next one after neon would be argon, right? And so if we want to write calcium, for example, instead of writing the whole thing out, we would go calcium. It would be a core argon, and then 4s2, and so on and so forth. And we use, of course, the inert gases because they have a complete closed shell. Well, in the end, what kind of science without exceptions? When we talk about atomic orbitals, we do not fully take in account the repulsive forces between the elements. For elements with incomplete d subshells, it is more advantageous to occupy the more higher energy 4s orbitals first. Why? Because it reduces the repulsive forces in the lower 3d orbitals. Okay. So the first row transition metals in the periodic table have the general 3dn 4s2 orbital. 4s2 is fully occupied despite the 3d being of lower energy. Another phenomenon that we talked about is that we can obtain lower energy by half-filled orbitals or filled d subshells. For example, we will most likely see the following scenario for chromium being D5S1 rather than expected D4S2. So we have when we talk about the full D subshell, again we would rather have D10S1 rather than D9S2, which is in the case of cuprum or copper. Or we will have D10S0 rather than D8S2 for palladium. Now, why is this? Well, because as we talked about the spins, we have a pair of spins, right? So it is more advantageous to reduce these repulsive forces with parallel spins than to fill in a lower energy orbital. So for gadolinium, for example, the ground state would be the base xenon, then 4f7, 5d1, and 6s2, right? And not 4f8 and 6s2. We would rather fill the d orbital rather than complete the f orbital. Exceptions. Well, with this, we will finish today's presentation. I will have a few more slides beyond this, but please disregard them. Thank you.